The Wolfram language has lots of built-in functions for doing things that commonly come up in programming, like the map function, for example, which can also be entered using the /@ operator. Map is basically a substitute for a program like this one, which steps through a list in an explicit procedural loop. Map still has to step through the list, of course, but map is shorter and more efficient since all of the overhead of doing that is handled inside the map function. Map takes an optional third argument for specifying the level within the expression where the function should be used. For example, this applies the function to the elements of a matrix. The level specification here indicates level 2 within the expression, which corresponds to the elements of a matrix. Another function that can be used for stepping through the elements of a list is apply, but apply works much differently. Apply works by replacing the heads of expressions, so the function could perhaps be called replace head. For example, this replaces the head f with the head g. There is a special notation for apply, which is the @ operator. Since the head of an expression is typically the name of a function, replacing the head has the effect of turning an expression into a different function. So for example, this shows apply and rule used to turn a list into a rule. Like the map function, the apply function also takes an optional third argument that works as a level specification. For example, this uses the optional third argument to apply a function at level 1 within the expression, which in this example turns each sublist into an expression with a head of g. This shows a typical application with apply used to turn a list of pairs into a list of rules. Applying a function at level 1 like this is a sufficiently common thing to do that there is a separate notation for it, which is this operator with 3 @ signs, so that input could also look like this. Another class of programs is handled by functions like nest and fixed point, which instead of stepping through a list are useful for programs that work by doing something over and over. The nest function does that by applying a function over and over, and there is a related function called nest list that gives a list of all of the steps in that process. A simple application is this result, which gives a formula for a few periods of exponential growth or geometric growth or compound interest of an amount a at some growth rate r, or nest list can give a list of values after each period. The fixed point function does something similar, but instead of applying the function a specified number of times, it applies the function until the result stops changing. For example, this shows a function that when applied over and over to a starting value of 1.0 converges to the square root of 2. There is also a function fixed point list that shows the list of values for each step in that process. Another class of programs are programs that in some sense involve a combination of stepping through a list and repeatedly applying a function. Programs like that can be written using functions like fold and fold list. This example shows a typical result from fold list. Fold list can be thought of as giving cumulative results while stepping through the elements of a list, and fold just gives the last element in the result from fold list. This shows a simple application. This applies the max function at each step, which ends up giving the running maximum of the elements in the list. While considering any of these functions, like fold list and so on, it is useful to note that the simplest applications of these functions can often be done more efficiently by other more specialized functions. For example, this shows map used with a function that adds x to each element in a list, but that same result can be obtained by just adding x to the list, which works because addition maps over the list automatically. This shows apply used to turn a list into a sum, which adds up the elements in the list, but adding up the elements in a list is a fairly common thing to do, so there is a separate function called total that does that more efficiently. This shows fold list used with the plus function to give cumulative sums of the elements in a list, which is also a common thing to do, and that can be done more efficiently using the accumulate function. Many of these more specialized functions take optional arguments, like optional level specifications. For example, this shows the total function adding up the elements in each column of a matrix, or the second argument in total can be changed so that the elements are totaled at level 2, which adds up the elements in each row of the matrix, or that second argument can be used to add up all of the elements in a combination of nested lists. For one last example of this sort of thing, this shows map and reverse being used to reverse the elements in each sublist, but reverse is another one of those functions that takes an optional level specification argument, so the same thing can be accomplished just using the reverse function and a suitable level specification. Returning to more general uses of map and apply and so on, a common feature of nearly all functional programs is the use of functions as the arguments of other functions. The first argument in map, for example, is a function. In the Wolfram language, a function can be specified either by giving the name of the function, as in this example where the function is specified by giving the name sort, or a function can be specified as a pure anonymous function, as in this example, which maps a pure function that selects the even elements from each sublist. Several functions have special operator forms, like in this example, which uses an operator form of the select function. Another way of specifying a function which merits some special attention is to use an assignment to define a new function and then use the name of the new function in the program. That approach is quite different really because it leads to a different way of organizing the program, since instead of having the whole program in one expression, a program organized this way is broken up into inputs that define functions and separate inputs that apply those functions. Assignments and function definitions are not part of functional programming. Any use of assignments like this is potentially confusing because it means that the behavior of one part of the program depends on assignments that happen in some other part of the program, but assignments can still be helpful for breaking up programs into more manageable pieces or for making programs more readable, even in otherwise functional programs. For example, here is a purely functional recursive program that multiplies the integers 1 through 5, so this computes 5 factorial. And here is that same program written using an assignment that defines the function that does each step in the recursion. The function f here returns 1 if the argument is 0 and otherwise multiplies the argument by the same function applied to the argument minus 1, which is a recursive definition of factorial. These two programs do essentially the same thing, but the assignment makes the second program shorter and makes it perhaps a little easier to see what the program is doing. Beyond map and apply and fold list and so on, the Wolfram language includes lots of other functions that mostly involve different ways of stepping through the elements of a list, so basically variations of map. For example, this shows a function called mapThread mapping a function over a pair of lists. That same result can be obtained in various other ways, such as with this input using map and transpose, but mapThread is often a more convenient way to set up a program like this. There are lots of other functions like this, including mapThread and scan and blockmap and mapIndexed and arrayFilter and outer and quite a few others. For example, this shows the blockmap function, which is used here to break a list into blocks of length 3 and then apply a function to each block. This sort of operation could come up in decimating data or reducing the size of a digital image. The blocks can be overlapping, as in this input, which applies a function to overlapping blocks of length 3, and that is the sort of operation that comes up in filtering data and digital images. The same result can be obtained using the arrayFilter function, which is specifically designed for filtering. A typical application might be something like this, which applies the mean function to each block and so gives the running mean of the data. That input includes the padding option, which controls how arrayFilter handles the blocks at the ends of the list. The default behavior without that option is shown by this result, which pads the list with copies of the elements at the ends of the list. That result can in principle be built up using map and various other functions, such as in this input using map and partition and arrayPad, but more specialized functions like arrayFilter and blockmap are typically faster and more convenient for these types of programs. That's the end of the examples for this section. A good place to find links to more information about functional programming is this guide page on functional programming in the Wolfram language documentation.